Okay, for a particular atom, whether it is hydrogen, barium, carbon, because it has their own specific atomic number which defines the proton number, which for a neutral atom, the proton number is always equal to the electron number. So, every single electron in this atom definitely has their own address. So we should be able to define the location of the electron for that specific atom. Okay, and it's called the electronic configuration. Okay, in order to define the electronic configuration, the scientists come out with the concept of quantum numbers, where each orbit in the atomic model. So you see here is the nucleus. Okay, and then the highest probability to find the electron at certain level of energy from the nucleus, we have orbitals, right? So the orbitals having its definite energy, okay, known as the energy shell or energy level. And then each and every of these energy level, you see, we have this one is the N1, the energy level 1, energy level 2, then energy level 3, and this energy level have their own subshell, okay? So the electrons can reside at different subshells in the atom. Okay, so using this wave mechanism, each electron is defined by the quantum numbers. As a human, we have our home, and then our house has its own addresses. We can address each and specific electron based on the quantum number. Okay, so quantum numbers dictate the number of states within each subshell. So you have shell and then you have subshell. So in the subshell, you have different states of the energy level. So there are 4 parameters defining the quantum numbers. One, we have the principal quantum number, N. Second, we have secondary or orbital quantum number, or also known as angular quantum numbers or azimuth quantum number, and refer as L. And then we also have magnetic quantum number, as well as we have spin quantum number to define the electron. For the principal quantum number N, so this principal quantum number N is related to the size of the shell, where the principal quantum number N can have the positive values from 1, 2, 3, and so on. Okay, as the N increases from 1, 2, 3, 4, orbital become larger, and it means electron has higher energy and less tightly bound to the nucleus. So it means that for a particular atom, when you have more electrons in the atom, it's going to have higher quantum numbers, because this quantum numbers is the place where the electron is going to reside. So as the number of the electron increases, so orbital also increases based the increment in the principal quantum number. So each of these principal quantum number having different energy, as we mentioned previously. So you see here, this is for the energy level 1, energy level 2, level 3, and level 4. So the energy is increases. So electrons that reside at the higher quantum number have higher energy and lessly bound to the nucleus. Okay, so you see increment in the distance of the electron from the nucleus. Okay, second is the orbital quantum number, or the secondary quantum number, the L. Okay, so if the principal quantum number, which is N, and we refer N as house, the number N is going to tell you how big the orbital of the atom and how many level of the energy that the atom has. So the orbital quantum numbers L is referring some sort like the rooms inside the quantum number N. Okay, so the possible value of L is always N minus 1. So if you have the quantum number, principal quantum number N is equal to 1, so the possible value of L for the atom with only principal number 1 is 1 minus 1, so L is equal to 0. Okay, the second quantum number is signifies the subshell, okay, which also denoted by lowercase, okay, as SPDF, okay. So you know N is the energy level or energy shell, and this orbital quantum number L is the subshell, okay. So this subshell is related to the shape of the electron subshell. So how many rooms can fit within the house, and what is the type or shape of the room that can occupy electron? So if you have N is equal to 1, so L for this one is only 1 minus 1, so it's equal to 0. So for the energy level 1, it only has this subshell S, okay. But if you have the N is equal to 2, okay, you can have L is equal to 2 minus 1 is 1, and also you can have 0. So you have 0 and 1, where 0 has spherical orbital, which is S orbital, and 1 is represent the P orbital. Okay, also known as polar orbital. Okay, we can also have d orbital or clover leaf. Say for example, when you have N is equal to 3, so you have L equal to 0, 1, and 2, right? So for 0, you have this subshell. For 1, you have this subshell. But for this one, you have this subshell where L is equal to 2. It's denoted as the D subshell, or it has the shape as the clover leaf. So previously, we know, right, how big the shell is from the principal quantum number, how big the house, and we know what is the shape of the subshell, how many rooms that actually can house fit in, and what is the shape, okay, based on the secondary quantum number L. So how many electrons that can reside in the subshell? Okay, so you have shell, okay, you have subshell, and each subshell has different shapes, right? Okay, so how many electrons can reside in each of the subshell? So to know this, you be able to calculate based on this equation. It's 2 times 2L plus 1, okay? So you see here, okay, say for example, for the N, the quantum number, principal quantum number N is equal to 1, okay, and you know the L is only equal to 0. So within the S orbital or S subshell, you only can fit in 2 electrons in this particular orbital. How? It's based on 2 is 2 times 0 plus 1. Okay, so it's equal to 2. So for example, your atom also has the principal quantum number of 2. So you will have L is equal to 0 and also L is equal to 1. So for the S orbital, you can fit in 2 electrons. So for this P orbital, you can fit in 6 electrons. Okay, how? Because the number is equal to 2 times 1 plus 1. So it's 3 times 2, so it's equal to 6. Okay, so as the example for the principal quantum number of 3, you can find that it also has the clover leaf orbital, okay, and then so it can locate 10 electrons inside the D orbital for the energy level 3, and so on, okay. So third quantum number is the magnetic quantum number, or ML. So the ML, the magnetic quantum number, is defining the number of energy states, because we know that electron, where it's located in an atom, is based on the energy level belongs to that specific electron. So definitely we should know for each subshell how many number of energy states that it can have. Okay, so for the total number of magnetic quantum number, it is equal or can be calculated based on 2L plus 1. Okay, for each orbital quantum number L. Okay, so the value of ML is given by the whole number, which is in between -1 plus 1. Okay, so it shows the orbital orientation. Okay, so for S subshell, there is a single state. Why? Okay, say for example here, right, we have n equal to 1. So you know for this one, n equal to 1, L is always equal to 0, right? So it only has S orbital. So for this particular S orbital, it only has this single energy state, 0. Okay. However, for the N shell, which is the energy level 2, you can have L is equal to 0 and 1, right? So for the 0, you have S orbital, and then 1, you have P orbital. So for this S orbital, it has single state. However, for this P orbital, it has 3 energy states. -1, 0, and +1. Okay. For this one, level energy 3, it has single 3s state. It has 3 states for the 3p orbital. Okay. 0, +1. And it also has -2, -1, 0, +1, and +2 energy state for the d orbital in the level energy 3. Okay, so you see from the nucleus, the electron that reside at higher energy level having increment in the energy. Talking about the 1s orbital only can have one state, which is spherical shape, right? So, how for the 2p orbital? As we know, it has 3 states of energy. So, the orientation of these 3 states of energy is given by this. So, you see, it is having polar shape, okay? So, the first shape is for the orbital known as the 2, because it's the level 2 energy, 2px. For the px orbital. So you see, this is the x-axis. So for the one beside at the y-axis, it has 2py. And then for the one which is in line with the z-axis is pz orbital. So for this particular orbital 2p, it has 3 energy states. 1, 2, 3. Meanwhile, for the one which is n is equal to 3, it has, along with the 3s and 3p, it also has 3d orbital, which has 5 different energy states. 1, 2, 3, 4, and 5. So why it is a 3D region? Because as we know earlier, based on the theory by Schrödinger, that the electron is residing in an atom at the probability region. So for this 3D orbital, this is the probability of finding the electron. Okay. Last but not least is the spin quantum number known as ms. Okay, so it specifies the value for the spin moment of the electron, which must be oriented up or down. At the specific state, okay, say for example 1s, only 2 electrons can reside at this particular state. One electron having up spin and another one having down spin. So one up is as plus half and another one which is down is as the negative half. Okay, for each spin orientation. So it's based on the Pauli exclusion principle. Each electron state can hold no more than 2 electrons which must have opposite spin. Okay, so this is the number of available electron states in some of the electron shells and subshells. So you see this one, n is equal to 1, 2, 3, and 4. And designation of the principal number, quantum number n, you can denote as KL and n. So the subshell either F, P, D or F. So each of the subshell or orbital, it has its own number of states, and then the number of the electrons per state is always 2 electrons. and then it has different spin for each particular state. So this is the summary of the quantum numbers, where we define electron in the atom based on this quantum number, N, L, ML, and MS. So this is the allowable value, and this is the property that's shown by each of the quantum number. Okay, so this is the example when you have N is equal to 3. Okay,